Hi, my name is Zach Parrish. I am a tech artist at Epic Games, and I'm attached to support and developer relations. What that generally means is that I'm never at the office. I'm always flying around to awesome cities like Montreal, visiting devs, and helping them all make their games better. Today, I'm going to talk to you guys about profiling and optimizing in UE4. So when I was asked to give this talk, I was really excited for a whole second because I gave this talk 2 years ago at MIGS. Some of you might have even seen it. It was cute. We talked about like the CPU profiler, the GPU profiler. We did some stuff in the engine, and it was all great. And so I was like, cool, I'll just resurrect that talk. However, I discovered really quickly that I've got a lot more that I should cover to make you guys really effective at keeping your games from slowing down. So I started adding on some of the things that I've picked up from visiting other licensees. And in time, my outline got way, way, way too long. So I actually have more information here than we can ever hope to cover. I'm going to go through some of this a little bit quick, mostly as review. When we get to actually using the tools, things like the CPU and GPU profiler, all of that stuff and how to use it, the actual buttons you click, it's all covered on YouTube already. So if you need actual step-by-step, go over there. Today, I'm going to bombard you with information, things you should know about keeping your games from slowing down. I see some of you have notebooks out already, and that's super exciting. You will need them. So here's what we're going to cover today. We'll start off with some profiling best practices, just getting your profiling environment set up. We'll talk about the profiling process, how we go about profiling things at Epic Games. We'll do kind of a highlight of the profiling tools that are available, the things that are in the engine to make your life easier. We're going to talk about blueprint optimizations, which is something I'm pretty passionate about. I love Blueprint. It absolutely changed my life because it allowed me to make games for the first time because I'm not a programmer at all. But we'll talk about how dangerous that can be. We'll talk about draw thread optimizations, so CPU rendering optimizations, GPU optimizations. We'll talk about a little bit for optimizing for device, so if you're developing for console. We're going to take a look at some network stuff, content streaming, and then I've got a few links that you guys should check out when we're all done. So starting off with profiling best practices. How are we doing on time already? This is great. I'm like ahead of schedule for the first time in my life. By the way, I just want to mention, this is a room full of game developers, and you're all here before 11 a.m. Give yourselves a round of applause. Right? Okay, so how often should we profile? How and when do we approach that? Profile early and often. You should not wait until the end. We actually run into studios that do a lot of their profiling and checking like toward the end as they're getting ready for a vertical slice or something very important, and that's generally a bad habit. You don't want to do it. Conversely, though, I always like to advise don't over-optimize. Early optimization, meaning like if you're pining over every little vertex and every little shader instruction, you're probably taking too long to accomplish too little. You should only be optimizing after you have profiled and you know that what you're trying to do is a problem. Now, some of you folks are here from the enterprise world, so yeah, you probably know that if you bring in a many billion triangle mesh from CAD or something, you know you're going to have to optimize that. But within that scope, don't spend too long until you already know it's going to be an issue. Make sure that you test on your target hardware ASAP. As soon as you know you're shipping on Xbox One, you should be deploying to Xbox One. I don't even care what your project is. If all you've got right now is just a little test scene, get that on Xbox One and get into the habit of deploying and testing over there. Also, make sure everyone on your team, as long as they're checking stuff into the engine, if they're ever touching the engine, they should know the basic profiling process. They should know at least 30% of what I'm going to cover today. That way, everybody on your team can be responsible for checking in content that is not going to slow your game down. It's actually how we do things at Epic Games. If you're checking in game assets, you are responsible for making sure we don't drop frame because of them. Next, profiling in a build. Generally, the safest way to profile is actually to do a full build of your game and profile from within that. If you try to profile within the editor, there's some noise there. We'll talk about that in a minute. So make sure that you minimize all of the other noise and things that can interrupt or make your numbers unreliable. So turn off everything you're not using. Make sure you turn off vsync. The command for that is rvsync 0. Quick thing, I see like the camera phones going up in the back. By all means, do it. I'll photobomb. Just know that we're recording this, so that will help, and we will find a way to get this slide deck out to everybody because it's too important not to. We're not going to hoard this. So next, turn off frame rate smoothing. If you haven't seen this, you should know where it is. It's in your project settings under General Settings, Frame Rate Group. If you noticed a couple of versions back, we made the project settings completely searchable. So just jump in there and search for smoothing. You'll find it really fast. Next, make a test build. This is something we discovered on Paragon. It was common for us to do development builds for that project, and when we did that, the draw thread was giving us unreliable numbers. So do a test build if you know you're going to be profiling. So profiling from within the editor, wall of text. You're going to see a lot of these today. I'm really sorry. I wanted to put in pictures, but there's just not enough room. So I wouldn't do serious profiles from within the editor, but for day-to-day stuff, if you're just checking in a new asset, a new shader, a new thing, new blueprint, whatever, it's okay. So feel free to do it. Don't be scared of it. Just know that you should be testing on a build often as well. So the editor is going to inject a little bit of noise into some things. You can mitigate that. You can make it kind of minimal, but just know it's still happening. So if you have to test from within the editor, one, make sure you're playing in standalone. Do not profile from within Pi. It's just a bad idea. Make sure the editor is set to not update in real time. That's up in your viewport, just upper left corner, drop down, uncheck real time, and then make sure you minimize the editor so it's using the least amount of computer resources. Turn off frame rate smoothing, which we already discussed, and then turn off VSync. Okay, so the profiling process, how we actually go about doing it. First thing you're going to do is identify the bottleneck. Find out where your problem really is. If you're trying to do anything, like if you start cleaning up shaders to speed up the GPU and it turns out you just had too many objects on the screen, you're doing it wrong. So make sure you know where the real problems are before you tackle anything. Your bottlenecks will either be the game thread or the render thread, and the render thread breaks up into the CPU or the GPU, and those bottlenecks will jump around as you optimize. So if you were bottlenecked on the CPU, you fix that, your next bottleneck might be to the GPU, and you might have to just kind of climb down the ladder until you hit target frame rate. Really quick check, and I'll bring this up a couple of times today. I think I'm actually going to repeat 2 or 3 things, but it's only because they're really important, is r.screen percentage. So if you haven't used this command while you're testing your game, if you want to know if you're, well, first off, you should probably know whether or not you are game thread or render thread bound. If you're on the game thread, you're making bad decisions in code or blueprint, and that's one set of problems. If you're render bound, then your assets are too much. You got too much. You're trying to actually draw on the screen. Your shaders are too high. It could be a million things, but that's a whole other set of problems. You should generally know which one of those things you have. If you want to know if you are render CPU or render GPU bound, set your resolution lower. You can do that with r.screen percentage, pull it down to like 10%, and if the game suddenly speeds up, then you were GPU bound, because you basically told the GPU to do less work. So once you know where you're bound, you want to search for problems in the bottleneck scope. I kind of already talked about that, but at a high level, game thread is code or blueprint. CPU is going to be for object count, draw calls, any culling operations, basically anything that sets up your scene. At a super high level, when you're rendering, your CPU is kind of building your scene, and then your GPU is going to draw it and make it look pretty for your monitor. Automation. Some teams like to set up automated tests to kind of figure out where, I've got a little bit of bleeding there. So some teams like to kind of automate the process of figuring out what things look like and if they're hitting frame rate. You can do this with a cinematic in a lot of cases. So feel free to do things like set up a sequencer fly through a camera pass that goes through the higher end sections of your game. You can run some console commands to record all of that data. We'll talk about what those commands are when we're done. Not all teams do this. We actually don't do this on Paragon. We have a couple of TAs who actually know our map, the monolith map, really well, and they know where to look for the real bottlenecks. So if you have folks like that on your team, cool. If not, something like a cinematic can really help. Next, how do we measure? We don't really care about the frame rate number so much. That comes as a matter of course. You should be measuring all things in milliseconds. So make sure you're using stat unit and not just stat FPS. If you feel better seeing the FPS number on the screen, you can type stat FPS to see that. I wouldn't recommend it. Every stat that you have running, every little metric is stealing just a little bit of your processing power, so I would turn it off. The stat unit, showing up over here, gives you a breakdown of time per frame. Now, it's not always color-coded. It's only coded if you're using a stat unit graph. I'll talk about that in a second, but it gives you frame. That's the total time for each frame. It gives you your game thread, which is your C++ or your blueprint, and it gives you your draw and your GPU, which is the CPU and GPU render time, respectively. Now, you can also use stat unit graph, and this shows a line graph for playback. We don't use it that much at Epic, but occasionally it's nice to kind of have it going because you can see if you have like a regular heartbeat coming through, which usually means something is getting in the way of your test. In a lot of cases, it's other software that's hitting your GPU for some reason. Next, part of our process, probably the first thing anybody at Epic does when they start profiling stuff is just to start throwing switches and see what gets better or see what breaks. So that's an easy way to find bottleneck issues, figure out where they are. Sometimes the best first step is just to go through this process. It's usually as simple as just showing and hiding different problem areas so you can see what things are hitting you the hardest. It's also useful to see what happens at different render resolutions, which we kind of already talked about. So screen percentage, talked about this a minute ago. We'll go to it in depth just so everybody's heard it and you understand. This is mostly useful for problems unrelated to the game thread, just rendering issues only. So you can use stat unit to figure out what your milliseconds are, and then use r screen percentage 10, or r dot screen percentage 10, or any number lower than 100. You could do 50 if you want to. I think 10 is usually what we use. So this takes your overall resolution, and you're only showing 10% of that. You're sending fewer pixels to the GPU is doing less work, and if your game immediately speeds up, it turns out that your GPU is overtaxed. So it's a great way to, like in just a couple of seconds, know kind of where your bottlenecks lie. Oh, missed one. So show flags. I'm often surprised at how often this is overlooked, but this is actually a really cool way to diagnose issues that you might have or different bottleneck locations. You can just turn things on and off in your scene. So you've got some commands for show or hide things like static meshes, skeletal meshes, and so on. Another common one that I didn't even list is instanced foliage. So you can just do show instance foliage. Quick story, while I was putting this together, I thought at first I might have time to dig into the editor and show you guys how to click on a couple of things. While I was doing that, you guys all, you're checking out like our launcher, you've seen like our Learn tab. On the Learn tab, there is this project called Landscape Mountains, and it's old. It's a little hang glidey game that we put out a while ago. And so I loaded that up, and I think the last time we saved it was 411. So I updated it to 417, and my frame rate was through the floor. And all I did was I said, show instance foliage and turn that off, and suddenly my frame rate skyrocketed. And what had happened is in the jump from 411 to 417, LODs broke. But I was able to diagnose that super fast just by turning something off. So make sure you're going through this process. If you know that you got a lot of static meshes in your scene, turn them off and see how much faster you get. You know it's going to get faster, but knowing by how much will help you understand, should I be lauding a little more aggressively? Should I be doing less transparency? Should I be tweaking my lighting, maybe use fewer lights, that sort of thing? So, diagnostic tools. Let's talk about what we got. Stat commands, we've already talked about a few of these. So these give you real-time feedback, statistics on different parts of the engine. There are a whole lot of them. We're not going to cover them all. I'm going to cover the ones that I use probably most commonly when I'm doing different profiles. Some of the more common ones you should know. So stat FPS and unit we talked about. Stat scene rendering is pretty huge. We have a whole slide dedicated to that. Stat GPU is relatively new, so you can get real-time feedback on what the GPU is seeing. We have stat streaming for texture streaming stats. Stat emitters and lighting are super great if you're trying to figure out how much your effects are costing. So stat scene rendering, this one's huge. Always remember this and always use it. This is the only place where you can see where your draw calls live. And draw calls are a major culprit for slowing down your CPU. Basically, you just got too many things on the screen. It can be individual meshes, too many materials, combination of both. Also, this is a good place for you to see how long shadows are taking to render, decals, post-processing, lighting. All of these things are broken down line by line. All you got to do is run your game, type stat scene rendering, and it's all right there. Stat GPU is relatively new. It's only been out for a couple of versions. So we've got a GPU profiler already in the engine, but this gives you real-time metrics on what the GPU is doing. It's not super detailed, but it can help you kind of get a high-level overview of what things are costing in general terms. So you can see, oh, my shadowed lights are costing a whole lot of milliseconds. I should look into that. So you can start maybe pulling back on the number of shadows you're casting into the scene. In most cases, you will still want to use the GPU profiler. That's really the only way you're going to find individual lights. So in GPU profiler, you only sample a single frame, and you break that frame down and see everything that happened. And using that, you can drill down and see specifically which lights are shadowing and how long each light is taking to render, and you can make more intelligent decisions that way. But at a really high level, Stat GPU can really help you out. Next, we have some optimization view modes. So these kind of turn you into the predator. They're pretty easy to forget about if you've just kind of been jamming, staring at the viewport all day. But there's a lot of really cool modes in here to kind of help you see how much you're doing in your scene at any given moment. So these view modes enable you to see different problems live right in your scene. And there's a couple of new ones that not everybody knows about that I find myself explaining to folks every now and then. So let's take a look. First off, shader complexity. Hopefully you've all seen this one. All this does is this shows you how much work your GPU is going to have to do to draw your shaders. Probably the most useful thing you'll get out of this is seeing where your overdraw is. By the way, this scene is horrible. When you open it up and you see this much red, you should generally be afraid. So the way this works is it's going to color code your whole screen from green to red. Green is generally good, red is generally bad, white is absolutely terrible. So just be really careful about this kind of thing. As transparency starts to stack up, you'll see overdraw issues and you'll see those colors really start to pop out. You can see some overdraw taking place out here on the horizon. It may be okay, just know that that's a thing and that overdraw gets really expensive really, really quickly. Next, we have quad overdraw. This is a relatively new view mode. It hasn't been in the engine very long, and I find there's a lot of folks who don't know it's there or don't know why it exists. So this is essentially a way for you to keep track of how polygons are being used on your screen. It's very important if you're on the forward renderer, mostly because of MSAA and how much anti-aliasing is going to be hammering all of the edges of your polygons because it's going to draw those pixels at the edges over and over and over. And there's a really direct relationship to how you're using your polygons to how efficiently and how fast you're going to be able to render in forward rendering, so keep that in mind. Even outside of forward rendering, though, it's a nice way for you to quickly visualize whether or not you should probably be lotting down. Let's jump forward for just a second, talk briefly about how this works. Your GPU, oh wow, colors are amazing there. So these are supposed to be kind of red or pinkish, maybe you can see that. So on your GPU, a lot of the operations that it's performing are taking place not on individual pixels, but on little 2x2 sections of pixels, which we refer to as quads. It's just an optimization, so you're not having to do quite so much work. If you are having to redraw all 4 pixels of a quad, you're probably not using the GPU as efficiently as it could be. So things like long triangles or really, really tiny triangles, as you can see, cause extra processing that is just going to be discarded, so you have to kind of watch out for that. The upshot of this, in practical terms, for all the artists out there who don't want to read up on GPUs, and you should, when you're looking at like an opaque object, at least on the deferred render, and you see a whole lot of green, what that means is all 4 pixels of that quad all had to be recalculated over and over. You should probably be lotting down. It just means you've got a lot of pixels that just rendered in a tiny little 2x2 section, so you should have a lower LOD that you're switching to. Next, shader complexity and quad overdraw. Those 2 last frames I was talking about, they just combine them into one. It's pretty cool to see this kind of stuff all in one frame, though I do find myself kind of jumping back to the individual ones to diagnose specific problems. But it is neat to see it all at the same time. Light complexity. I love this mode. So this allows you to visualize the cost of scene lighting. It's just direct lighting, so it's not really giving you the cost of shadows. So one of the major causes for GPU slowdown is the number of dynamic lights that you're trying to draw at any given time, and this is a great way to quickly visualize that. So if I walked into this room in this game and suddenly I was like, why is the game getting slow? I would switch to this view mode and go, oh. So the idea is that it color codes on its way from cool up to warm, up to nuclear white, and where you see white, you should really be kind of rethinking your approach, probably. Next, light map density. Light maps are awesome. They're a way for you to handle your light bakes in an intelligent way. I do often find that folks, if they're not paying attention to it, will keep their light maps very high resolution, a lot higher resolution than they probably need. In a lot of cases, your light mask light bakes really just kind of need soft, gentle shadowing to look really nice, and you probably don't need super high resolution on everything. It's also just easy to lose track, which is another place where this view mode will save you some time. Instead of like having to go through a like a spreadsheet or click on a whole bunch of things and try to figure out what their light map resolutions are, you can just turn this on in the viewport and immediately see where you might have problem children. Like here, this is just an outline around a door. It's very flat. I would probably immediately go change that and set that to a lower res. And if you build up a habit of keeping things as low res as you can possibly get away with, your light bakes will go a whole lot faster. Next, stationary light overlap. It's an easy one to also forget about, especially when you start to get a whole lot of different things in your scene. So when you're using stationary lights, as most of you probably already know, you can only have up to 4 stationary lights affecting any given object. Once you go beyond that, the 5th light will be converted back to a movable light, so it's fully dynamic shadows. It's very expensive. The engine does that switch for you, and it does that based off radius and brightness. Basically, it tries to figure out what's the least important light. I'm going to turn that over to dynamic. You don't want that to happen. This view mode is basically going to yell at you, as you can see here, and say, hey, you have too many stationary lights in one area. Also, this is an important point on this one, is if you have a stationary sun, which a lot of folks do, if you have like a non-real-time time of day and you used a great big stationary light for a sun, great. You now only have 3 lights left for every other object in your scene. Just be aware of that. Next, LOD coloration. So I did use this in the landscape example I was talking about earlier. So you can actually see the trees are all remaining white out on the distance, so none of them were LODing. This does exactly what the name implies. It just takes your entire scene and it color codes it based on how you're LODing. If you're just trying to figure out why your CPU is slowing down, you can learn a lot just by turning this on really, really quickly. Next, some profiling tools. Now again, we're going to be covering just the session front end for CPU and GPU profiling. We'll talk about the GPU profiler. We're not going to do individual mouse clicks. I'm really sorry. I wanted to. There just wasn't a whole lot of time for it. But we have a lot of really cool tutorials online to show you how to use those. And most of you don't have your laptops anyway, so it's all good. So CPU profiling takes place with our session front end. We have a profiler tab in there. It's an integrated tool that allows you to keep track of what's going on each tick. It's a good way to get code and blueprint performance, basically any of your gameplay code. The way this works is it measures a segment of time. So you'll start playing your game, and you'll fire off 2 different stat commands that you should know about. They are stat start file and stat stop file. In between the times that you put those commands in, the game is recording everything. You can then open up the session front end, you can load up that recording, and you can see everything that happened on every tick. You can look at individual frames, or you can look at an average over a given selection of frames. It's very, very cool. My favorite thing about it is you can actually dig down into your world tick. You can see how long individual blueprints are taking on the game thread. You can go all the way down and see how long individual nodes are taking to process. So if you've been like maybe writing some of your own blueprint nodes, or you've got engineers who've been helping you with that kind of thing, you can see how long their work is taking to actually process on the CPU. Now the session front end can also be used for CPU and or CPU rendering as well as GPU rendering as well. On the left-hand side, all of the rendering operations are listed off as well. You can see how long they're taking in milliseconds. Super, super useful tool. Next, the GPU profiler. So the purpose of the GPU profiler, as it runs right off the screen, sorry about that. It's just to take a single snapshot of a given frame while you're playing and give you a breakdown of how long different aspects of that scene took to process. It's pretty easy to use. You can just hit Control-Shift-, while you're running in the editor, or you can use the command profile GPU, which is not up there on the slide, but you can just type it out, profile GPU, and it'll bring the command up. If you're running the editor, it will open this window, and you actually get this visual breakdown. If you're in a build and you're not running the editor, it's going to dump all of the same information out to the log. So you can just take that log, open it up in any text editor, and see how long things are taking. It's super useful because it tells you how long like the base paths for actually setting up all of your lights and materials are. It tells you individual times for lighting, for shadows, tells you how long post-process is taking. And up here at the top, it actually has a bar graph that you can mouse over and see what portion of the scene render is taking the most time just at a glance. Super, super useful. Next, tracking slow frames. So how do you know where slowdowns are happening? So we have a command specifically for knowing where your game is hitching called dump hitches. So you should know about this one. The command is used to dump any hitches that run over a given time in milliseconds. You can set that number with T hitch threshold. So you'll basically say, all right, set that to 0.05, and then when you run dump pinches, it'll throw into the log everything that took longer than 0.05 milliseconds to run. It's a great way to track down things that are running over a given amount of time. At the bottom is an example of how we use this to create reports for frame rate on Unreal Tournament. So this is actually a report that goes out every week. Now we also have Mem Report. There's a really cool blog post on this, so I'm not going to go super far into it. Just search Mem Report over on our blog page. But essentially, this gives you a breakdown of how memory is being used in your game, so you can see out-of-memory issues and make intelligent decisions from there. Start and stop FPS chart give you a really cool chart for you to figure out how your frame rate may be increasing or decreasing during different parts of your game. If you combine this with a level sequence, like a camera fly-through, it can be a really nice way to kind of automate where your game is getting slow and know where parts of your environment are starting to take a hit. All right, blueprint optimizations. How we doing? Oh man, chugging through. So Blueprint is my favorite thing. It is the coolest thing since the other side of the pillow. However, the neat thing about Blueprint is it makes it really easy for visual people, for artistic people, and non-coder people like me to make their own gameplay logic. And in a lot of cases, not every case, but in a lot of cases, those are the last people you want touching gameplay logic. So it's easy for people to make bad decisions. So often when I go and talk to folks about using Blueprint, there's a few common problems that especially beginners run into, and we're going to kind of hammer on those. And yeah, I do generally refer to it as keeping the kids from eating the crayons, but man, the green crayon tastes so good. All right. So blueprints, again, we talked about it. They make it real easy for folks to do bad things. The best results we find come from some sort of mentorship. If you're at a studio and you want folks to be successful with Blueprint, have them sit down with engineers from time to time. Ideally, have an engineer go shoulder surf every now and then, or review the blueprints that they're making and smack their hand when they do something bad. The engineers, how many of you are programmers? Raise your hands. We can still be friends. Your engineer, if you are an engineer or the engineers on your team don't want to do this. They don't want to explain why you're making bad decisions, I assure you, but it's better for everyone. And in the long run, it'll take those visual people who aren't used to thinking like coders, and it will make them more efficient. So take the time to show them why they're doing the dumb thing. So some common challenges that you will run into are reliance on tick functionality. I love tick. You can just plug whatever you want into tick, and that thing just magically works. And you should never, ever use it in Blueprint. If you think you should use it in Blueprint, you should not use it in Blueprint. If you try to use it, you should probably be smacked. So overuse of expensive functions, things that iterate on many objects, and abuse of hard references. Now, all of the engineers in the room are all kind of probably nodding, and they're like, yeah, every scripting language in the world has these exact same rules. And that's the thing about Blueprint that the visual and artistic folks kind of forget. Blueprint is just a scripting language. It lives on its own VM layer. It's got its own kind of layer of processing that has to take place, and so it's slower than native code, and you have to follow these rules. So we'll talk about how to get around some of them. Relying on tick. Ticking means you're calculating on every frame. You might think you want that. You probably don't want that. You certainly don't want it in a scripting language. Blueprints should almost never, ever need to tick. Sometimes you'll run into something, maybe updating a material, or you're doing like a HUD for a fighter jet game, and you really, really think that that should be updating on every tick. You're probably wrong. It could probably update something kind of slow, like 20 times a second or 10 times a second, and nobody would ever know, but we'll talk about that in a minute. Remember to uncheck enable actor tick in your class defaults on every blueprint that is not ticking. That's an easy one to overlook. So it turns out, since we designed Blueprint to make visual people happy, we wanted them to be able to plug something into tick and see that thing work. So all blueprints by default are ticking. So turn that off. If you're not using tick for any reason, just go up there to your class defaults and disable actor tick. Next, some alternatives to tick you should know about. Look into timers. Maybe use timelines. It depends on what you're doing. If your thing needs curve-based animation, maybe consider timelines. There's cheaper ways to go about it if you're doing anything linear. Manually enabling or disabling tick on demand is also super cool. So let's say you did write something, and you're like, you know what, this has to tick, damn it. I know my engineer told me not to, but it just looks so much better when it's ticking. Cool. You can actually leave tick off until the moment you need to do that thing, enable tick, the tick function will just run, it'll do whatever it's supposed to do, and when it's finished, you can disable tick, so you're only doing it when you absolutely have to. And if you do that, make sure that you at least think about adjusting tick frequency. This is also available in class defaults. By default, it's set to 0.0, meaning you're ticking on every single frame, but if you pull that down to like 0.1, you're now only ticking that actor 10 times a second, so use that intelligently. Expensive functionality. So some functions in Blueprint are just expensive by the nature of how they work. Things like get all actors of class, things like spawning objects into the world, or anything that needs to iterate over a large list of objects. I have actually been to studios where I have found folks getting all actors of class, plugging them into an array, doing a for each on that array, and doing a loop on each thing in that array, and doing that on tick. And can't quite figure out why when they run with that blueprint, they suddenly drop to 5 frames a second. And they tell me that our shit's broke. It's awesome. So try not to use these at all if you can get away with it. If you can find ways to not have to query the scene for a big long list of things, great. If you can have those things report in so that like, hey, basically do their own roll call. They call up to a master class or a manager and say, hey, I exist. You should make a note of me. That's always faster. But that's the kind of thing you will learn from mentoring with an engineer, so make sure you're doing that. If you have to use things like this, like know the tools you have on hand. Make sure you know about T-sets and try to utilize those. Try to find very seldom times to do the heavy stuff. Maybe at begin play, maybe after a delay on begin play. It kind of depends, right? Like sometimes if too many things are using the begin play to do all the heavy stuff, it can take a while for your game to start, so just be careful about it. Also, be aware of heavy construction scripts because they can really kill your spawn times. Just consider placing that stuff in the world beforehand. Also, another one that I didn't list is, I think we'll cover it in a later slide, watch out for any blueprint that has a whole lot of components because it takes a really long time to spawn those. Okay, so this one is not obvious, and I run into a lot of studios that suffer from this one. So this is using hard references in Blueprint. So it's very easy for blueprints to generate references to each other. And the problem with references is when you load a given asset, like a blueprint, into the game, if it has references to other blueprints, it has to load all of those too. And if all of those blueprints have references to other blueprints, then those have to load in all their things too. And this can actually spiderweb into a situation where when you bring in your game character, you just loaded 5/8 of your game all at once. And you can't understand why load times are bad. And you call up Epic and you're like, hey, your stuff's broke. So watch out for this, and it's really easy to do. It can sneak up on you. So if anybody ever use cast nodes in Blueprint? There are like 1 or 2 people ever use Blueprint in this room. That's awesome. So cast nodes actually make a hard reference. So they're fine to use if you know you need them. That's great. My example here is like if you've got here you go. If you have a pickup class, like, I don't know, a health pickup or something, and when somebody runs over that, you want to cast to the player to make sure that that was the player, great, that'll probably be fine. But if, on the other hand, you did something like the player has to cast to every different pickup type that might be in the game, that's probably inefficient. So start thinking about it in terms of flow of information. Also, make sure you use Blueprint interfaces for that kind of thing. So the easy way to solve that problem is just to get the hang of just throwing interface messages over the wall. And if the receiving class understands what to do with it and implements that interface, great. If they don't, it won't crash your game. So basically, you can cast if you need to or get a reference, but do it to like a generic class like actor, and then just send an interface message to that actor. Other Blueprint optimizations. So these are just kind of general tips for anybody ever touching Blueprint. Avoid doing too much of any one thing. So it's the same rules of any scripting language. So watch out for too much functionality in one class. There's a studio that I ran into a very long time ago. They modified the editor so that if you added 100 nodes to any given blueprint, the moment you added the 101st, a modal window popped up that said, go get a programmer right now. It's a real thing. I was kind of impressed, but you don't want to have a whole ton of functionality. Now, on that note, if you played Robo Recall? So most of that game is actually done in Blueprint. It's actually pretty cool. So there's some generic classes on the back end, but most of the functionality is totally defined in Blueprint. And if you open up those blueprints, there's a whole lot there, but just understand that took us a lot of tweaking to get just right. Make sure you avoid class hierarchies that run too deep. Watch out for too many components within a class. It just makes those classes expensive. It makes them hard to spawn in. If they are scene components, that can actually make them hard to transform around because we've got to update all of those on every frame as well. Avoid too much high-end math. I have seen folks that they're really proud of some really cool math equation they did with traces or something in Blueprint, and it turns out they went through a whole bunch of effort to like recreate dot product or something. So don't do that sort of thing. We actually have a math expression node. If you haven't seen it, right-click, type math expression. You can actually just type an expression into it, and it'll build the graph for you on the back end. And that system is already optimized to go fast. So if you have to do high-end math, try to do it that way. When all else fails and you just can't make your blueprints fast, call one of the many engineers in the room right now and just have them nativize it. Generally, that in our case, that means they build a brand new class entirely from scratch by looking over their shoulder, mocking you for what you did in Blueprint, shaking their head in disappointment, and doing the whole thing in 3 lines of code. And that's fine. Then you can just reparent your descending class up to the new native class, and for the most part, stuff should just work. All right, knowing what actors are ticking, there's actually a command for that too. There's dump ticks. So this will just list off everything in your scene that is ticking right now, and you probably can't read it from back there, but it tells you how many tick functions are being used, how many of them have tick enabled, and how many of them don't. So that can be really, really useful as well. All right, so that's all the blueprint stuff. Now we can move on to the rendering stuff, the place where you can really start to make your scenes get slow and terrible. So we'll start with draw thread optimization. Stuff on the CPU. It's exciting. Bottlenecks at the draw thread are usually caused by things like too many draw calls or occlusion queries, simulating too many particles. It really boils down to just attempting to do too much stuff on your scene at once. That's really, every time you see the draw thread get slow, you should be thinking, I'm doing too much. Find everywhere you can to put fewer things on the screen. It could be fewer objects. It could be fewer vertices by using LODs. So just think in that direction. Know about the Actor Merge tool. So this is located under Window Developer Tools. This is going to take a selection of meshes and combine them into a brand new asset that will replace the original in your scene. So we use this a lot to just cut down on the total number of draw calls. The cool thing about doing this is it actually makes a new mesh out of whatever you had selected. And if you want to, you can open that mesh up in the static mesh editor and then start doing reduction and LODs on it if you'd like to. It does work best with many meshes that have the same material or as few materials as possible. If you try to combine 20 meshes and each one has its own individual material, you're not really getting a huge benefit out of that because every material is going to make another draw call anyway, so you're kind of right back where you started. Now, there is an option in the Actor Merge tool to combine materials into one. It basically just folds everything together into one material by atlasing all the textures. Just understand that requires a Simplygon implementation to use that functionality. Next, instant static meshes. These are awesome. So these are a mechanism for creating multiple copies of any given mesh, but have them all be part of the same mesh object. The only catch to them is that right now you can only create them in the editor by way of Blueprint or your own maybe a native code class that'll do it, like if you want to write an art tool. But it's pretty easy to make a blueprint that'll do this. Generally what I do, or what I'll end up walking somebody through, is you create 2 different blueprints. Like one will be a placement. So this placement blueprint does nothing. It just holds a static mesh component that you can point at any mesh in your game, and you can use that to figure out like how all of the tables and chairs get positioned. Then you have another blueprint that just collects all those guys together, figures out how many meshes it needs, and then populates a static, instant static mesh component to replace all those things. And then if it's really clever, it'll at least turn off, hide, maybe delete out the placement meshes that were already there. Generally, I like to just kind of hide them out. They weren't ticking anyway, and that way, like if I change my mind later and I need to replace some things, it makes it easier. Also consider hierarchical instant static meshes. So these are kind of an advanced version of instant static mesh. They handle their own occlusion and visibility. So it's essentially what we're using under the hood for foliage. Hierarchical LODs. So know about these. We use them a whole lot in Paragon, and Paragon's an important case study in a lot of in a lot of situations because it's a very pretty game that has to run at 60 hertz on console at 1080p. So know about that. So hierarchical LODs allow you to take multiple meshes and combine them and then reduce that single mesh that has then been combined. So you'll have 20 meshes. The farther you get away, they all lump together, and then that one big mesh will get simpler and simpler as you get farther and farther out. It's really cool for things like cities or any large conglomeration of complex things. It does not support instant static meshes, so know that going in. It will fail if you're trying to add instant static meshes in. I've run into that a couple of times, even on this trip, and it does require Simply Gone to do its thing. Next, GPU optimizations, making the most of all the pixels you're drawing on your screen. So vertex shader optimizations, be careful of how much you use things like world position offset. By all means, don't be afraid of it. We use it all over the place. Just know that it has a cost, and that cost can add up over time, and if you have too many objects using it. Vertex color can also get costly. Actually, on Paragon, we ended up removing vertex color from all of our assets, and we just put it in manually where we need it, just because the cost of it was adding up too much. Pixel shader. So I've just got some simple do's and don'ts to try to make your lives a little easier instead of doing a whole bunch of individual case study-like problems. So don't use too much math. Again, there are the folks who will make really high-end math equations just to solve some cool thing on a pixel shader, but that stuff gets really expensive really quickly. Don't use too many textures. Obviously, the engine will yell at you if you do that anyway. Watch out for procedural functions. We make a lot of really cool nodes that will just do really cool effects in your shader. Like the noise is my favorite one because we have a really cool noise node in the engine now. I wouldn't use it for anything I was shipping, just so we're clear. You can definitely use it with render target bake to actually make textures. Like you can make tileable textures with it, but I wouldn't leave a noise node in anything that I intended to have on my screen. Too many material layers is another common one. That's only because material layers, you guys, if you played with them, a material layer is a way to specify a type of material, something like fabric or skin or denim or leather or steel, and then you can just layer those all together to make whatever your final thing is. We use this all over the place in Paragon for characters that have, like a bit of armor and whatnot. But you have to be a little careful because what you're essentially doing is you're taking that final material and you're adding all of the instructions of all of those material layers. So if those layers themselves are really complex, it can get to be pretty expensive. Watch out for reliance on if statements. I've run into a lot of cases where folks believe that if you have an if statement, you're using one side of the graph or the other. You're not. It has to calculate both sides. Pixel shader, good ideas, do's, things you should be doing. Use texture lookups instead of using math if you can get away with it. Anything that you can bake out into something like a lookup table, you should be doing that. Compress grayscale maps into single textures, so you can stick a grayscale map into a channel for RGB and A. You'll see we do this a whole lot in the engine. Minimize your layer usage. Don't use any more than you absolutely have to. And when you do like material layering like that, try to keep the layers themselves very simple. So don't worry about putting like maybe a high-end normal map for your entire character inside here. Just layer that over the top of the material. Little things like that can save you some time and hassle. Use switch parameters to turn off the things that you don't need, so your individual instances of a material can be a little simplified. It does require you to compile another copy of the material. So if you use something like a switch parameter, and for instance A you have it on, instance B you have it off, that required you to actually compile both copies of that. But at the end of the day, that's better than not. Next, material instruction counts. If you make content for the engine, this is one of the slides that you might want to maybe snap a quick picture of. So always pay attention to material instruction counts. This number is not accurate in the material editor until you click apply. That's an easy misconception. So oftentimes I will open up a material, and just to be safe, the first thing I will do is move a node and click apply just to recalculate and make sure that I know what those numbers are. On Paragon, we actually have an instruction budget, because I've had a lot of folks ask me this. For characters, it's about 350 instructions. On the environment, it's 150 to 200 with an absolute max of 255. If you go anything over that, you got to start chopping down. It's cool to pay attention to this too, because depending on what you're trying to do in your shader, you'll see some operations will really make these instruction counts climb, and others you almost don't feel. So just keep an eye on that number. Dealing with overdraw. So overdraw is probably one of the leading causes of murdering your GPU. It'll just slow your game down terribly. And the only trick to it, the only thing you can really do about it is either do less, so have fewer blades of grass, have fewer visual effects, have fewer sheets of fog, and so forth, or which you'll probably have to do that anyway, just so we're clear. But also minimize the geometry area for overdraw. So you guys all see the kite demo we did at GDC a couple years back? So that had a whole lot of grass in it, grass and flowers as far as the eye could see. And what we ended up having to do was take the polygon sheets for the grass and we actually cut them out all the way around the texture. So there's almost no overdraw edge around the whole thing. So don't be afraid of doing things like that. For particle systems, because a lot of your overdraw will come for effects, make sure you are always using the particle cutout property. You should never not be using this for translucent particles. It's pretty simple. It's in your required module. It's easy to find. You feed this a texture, and it will snip out your particle sprite sheet to reduce it down to the size of your texture, and it'll key off of alpha, it'll key off of brightness, or any one of your individual RGB channels. Next, managing texture resolution. You can author textures at pretty much whatever resolution you like. I should be really careful when I say that. Like, yeah, 8K textures are probably over the top, but I guess you could do it if you really wanted to. Just keep in mind that you're probably not always using full resolution. The engine is going to try to MIP those things down, in some cases very aggressively, which kind of leads back to always make sure that your textures are all in powers of 2 so that you can MIP them down. Use the texture streaming views to see what level of MIPs you're using for any given texture. We'll cover those just a little bit at the end. You can use the statistics panel, so it's under Windows Statistics, to see what textures you have loaded in your level at any given time. You can see what resolution they were authored at, and you can see what resolution they're actually drawing at. You can actually see what MIP level they're using. So you can start to notice patterns really quickly that way. Like, you'll be like, oh, cool, we have this really awesome 8K texture on this rock that's only ever using like this tiny little 64 by 64 MIP. And so you can start making decisions like that. Next, lighting considerations. So dynamic lights are expensive. Everybody knows that, hopefully, at this point. Small, unshadowed lights are relatively cheap, but you want to be careful how you use those too. You can have a lot of them thanks to the deferred renderer. If you're on forward, the rules are a little bit different, but not so bad. So a couple of things. So minimize the number of dynamic lights at all times. Try to keep it as low as you can possibly get away with. I don't talk much about static lights. You bake those and you forget about them. They're really just the cost of your light maps at that point. Minimize the number of things dynamic lights have to affect. Dynamic lights, particularly if you're using dynamic shadows, they have to process the actual geometry of whatever they're casting shadows on. So if you're doing a dynamic light against a very high resolution piece of geometry, that gets expensive too. So know about that sort of thing. Minimize dynamic light radii. Keep those radii really, really tight. Cast shadows from as few dynamic lights as possible. I still run into studios every time I go out for visits, folks who just have it's better. It's usually not every light casting shadows, but usually a lot more than they need. Your scene can usually look good with very, very few shadow casting lights. Watch out for stationary light overlap. It will sneak up on you because it's easy to lose track of. Obviously, bake lights wherever you can. I know that baking takes time. Artists tend to hate that. So at Epic, we have nightly light bakes. We generally only do like preview or at least low-quality builds for the most part. We only do like a production build right before we ship something. So keep it simple for as long as you possibly can. Don't assume that you need dynamic lights. You probably don't. I've run into folks even on this trip who are like, yeah, we had to do dynamic just because. And when you look at their scene, they're in a world that's very static. Things aren't changing. They're not knocking down walls very often or anything, so you should probably be baking that whenever you can. Use mesh distance field shadows. If you can afford mesh distance field, they're pretty cool. You can't always. Like, not all projects are right for it, or sometimes on console they can get a little heavy depending on what you're doing. But we use them on Fortnite, and Fortnite just went out on Xbox One, so they're pretty cool. They give you distance field AO, but they also give you nice distance field shadows, which we use at a distance. See what I did there? So watch out for dense shadow cascades. Make sure you're aware of shadow bias. It'll clean up some artifacting. You can overuse it as well. Generally, if you're doing like a dynamic sun, you'll want to limit the angles that your sun can move just so you don't have to bias too much. And always keep your light map resolution as low as you can, which we kind of already covered. So lighting considerations, just more stuff on this. Avoid light functions if at all possible. They do look really cool. I mean, we use them, right? Like if we need to do cloud shadows across the ground, we'll generally stick a light function up on the directional light. Just know that kind of stuff gets expensive, and don't do it if you don't have to. IES profiles are much cheaper, so use those if you can. Lit translucency gets really, really expensive. One random case study, I was helping a studio out with some game they were putting together, and they couldn't figure out why lit translucency was biting them so hard, and it turned out, do you guys remember, like, we released a lot of content when UE4 dropped. We have that one effects cave that looks kind of Skyrim-y. So there's a lot of lit translucency particles in there. And what they had done is they had migrated that into their project and then copied it over and over again to make ground fog. And I found that. I was like, okay, yeah, just because we did it to show off how cool the engine is doesn't mean you should ship with it. Also, just a random thing, just because we did it because it's cool in a tech demo doesn't mean you should ship with it. So I've said that to everyone. Next, cull dynamic lights out as early as possible. Turn them off if you can. Spotlights are cheaper than point lights, at least by a little bit. And don't be afraid to completely fake shadows. Several of our VR operators will either use capsule shadows because they're cheap, or in some cases, we will actually do completely fake, old school, like 1997 blob shadows where we have a little piece of geometry with a modulated material on it. Optimizing for device. I'm going to go through this a little quick because of time. You do have some device optimizations because we try to promote the build once, deploy anywhere technique to keep your life easy. You shouldn't have to be doing a lot of bespoke individual assets for the different platforms. All things being equal, this just works. Many of the content tools in UE4 have options for making intelligent content that will cook to many different platforms. So if you didn't know, actually, real quick, a lot of the things I'm going to talk about are stuff that we're using on Paragon to keep it running at 60 hertz on console. So make sure you're aware of the device profiles editor. It gives you access to a big long list of every device you're probably ever going to ship on. So every mobile device, every console, if you already have the console stuff installed in your editor. And you can change CVARs based on that. So you can say, like, on PS4, I want lower quality shadows, or I want lighting to be calculated in a lighter way. So this enables for, obviously, lower performance devices to make different decisions. But a nice thing about this is you have some per-device material optimizations as well. So there's a quality switch node that allows you to take your materials and set them to medium, high, or low quality. And you can use a CVAR to switch out which one of those inputs you want to use. So if you go into your material, you search for quality switch, you'll see it has a default setting, low, medium, high. What you'll do is you'll use several of these into the different inputs of your material. And then when you cook out, you can say, like, on PS4, we're going to use the medium version of that material, and on PC, we're going to use the high version. It's actually exactly what we do on Paragon. A quick thing on network optimization. So common problems for networking, it's usually pretty obvious. You're doing too much and you're doing it too often. Obviously, replicate as little as you can. The big thing I'd like you to walk away from here is knowing about the net commands. So net dot, and there's a few of these. If you go into the console, type net dot, you'll see the big long list of them. Probably the most important is net dot dump relevant actors. This command is actually just cleaned up for 4.19, so it's going to work a whole lot better. Often, you will need to run these commands on the server to know what's actually going on. That's easy. That's just cheat space net dot whatever your command is. So just be aware that you can do that. We have some features coming soon to 4.19. So some of our battle royale efforts are trying to make the engine better for everyone. So we have statnet. This has been improved for 4.19 to show more reliable data, and it can be used from the client reliably. And we have network relevancy view mode coming in 4.19. So this essentially color codes your screen so you can see what is currently relevant, what is not relevant, what is dormant and will be relevant. Really nice for identifying what things are affecting your bandwidth. Content streaming. So, well, again, we'll go over this kind of quickly as well. So texture streaming into and out of your scene can cause pops if you're not really managing it or staying on top of it. So we got a couple of tools to make this a little easier on you. We have the texture streaming view modes, which we added relatively recently to the engine. I think they went in I want to say 4.15. And then we've got the stat streaming metrics. So we have primitive distance accuracy. You'll find this under your view modes. Under optimization, you'll see that there's 4 different streaming view modes. So primitive distant accuracy is going to show you how efficiently you are MIPing your textures based on the distance from the camera. So it's just a way for you to kind of see what decisions the texture streamer is making just purely based on distance. It color codes to let you know if you have too few MIPs, too many MIPs, or you're right on target, which is going to be white, what you should probably be shooting for. We can do the same thing based on mesh UV density. So the way you lay out your UVs is also taken into account by the streamer. So this is just a way to do the exact same thing, but based on how your UVs are laid out on your objects. We have material texture scale accuracy. So if you've been scaling your UVs to change the way textures look, that gets taken into account by the texture streamer as well. And this view mode is really just about showing you errors. So areas where you have like the worst possible outcome that you might need to check out your texture scaling. And then finally, we have required texture resolution. This just shows you the difference between what the GPU wants to render, what it thinks it should have in terms of texture resolution, and what it's actually getting. And again, it's color-coded to help you see where you should maybe be making textures to your texture res. Finally, we have stat streaming. So this is real-time metrics on how much memory you're using based on what the streaming system actually thinks it needs and what it actually has, how much memory is being used, so know about that. Level streaming. So most games should probably be using level streaming to some degree. It's not always about breaking your game up into individual levels in the classical sense. We actually use it more like a layering system for most of our games, but it is nice to be able to stream out the parts of the world that you don't need. We have a lot of documentation and a lot of examples on how this works. Be sure you've checked out the Content Examples project if you've never really played with it. Level streaming is also how we collaborate on levels at Epic. So if you're not doing this, you should. Every now and then I run into studios that haven't started doing it. So like, for example, in Paragon, which is really only one world and we don't need to stream a lot of it in and out very much, we break it up into a level for lighting, base geometry, collision, foliage, and this is kind of a simplified view. The cool thing is actually in Paragon, we have a gameplay level that is all of your towers, all of your spawners, everything that makes Paragon a MOBA is all on one streamed level so that it's really easy for those things to communicate. World composition is another approach for level streaming. So it's really designed for very, very big worlds. We gave this a lot of polish when we did the kite demo a couple of years back. It takes a large piece of landscape and breaks it up into a grid, and then it'll automatically stream in and out as you move through it. It does not work with old school streaming volumes. Like our Unreal Engine 3 streaming volume system immediately stops working when you use world composition. Just know that it's very easy to make a blueprint that will do the exact same job. So really, you can hammer together that blueprint, use those in lieu of old school streaming volumes, and everything works exactly the same way as it always did. Now, I got some further info, stuff you should at least be aware of if you want to get into this and kind of review some of the things we've talked about. How to scale down and not get caught is a talk that Martin Mittring, formerly of Epic, did several years back. It's still on YouTube. It's definitely worth checking out. It's how we got our Vulkan demo put together a few years ago. The Tech Art Aid videos on YouTube. Oscar Swearword, I've checked out this guy's stuff. It's actually really good. Very, it's informative in that he breaks down all of the different passes that are taking place on the GPU. It's really juicy stuff. And then check out, read articles. Read as much as you can about how GPUs work. And there's a really great one that I'm kind of in love with. It's GPU performance for game artists. So it's on fragmentbuffer.com. So this guy has taken all the different passes of the GPU and broken them down to make them make sense for how you're building your content. And it's really, really useful. So I have killed off pretty much all the time that I have. So I'm not going to take questions right now. I'm going to jump off stage. But if you have questions, please come and find me. I'm going to be up on the terrace. Be happy to talk to you guys. Thank you so much for dealing with my walls of text and barrage of talking to you. You were all great, and enjoy the rest of Dev Day.